House robber 3 is again a slight modification from house robber 1, where we remember in house robber 1 we have houses on a straight street, and we use an integer number to represent how much money is in each house. And the goal is to rob as much as money without robbing houses that are next to each other. However, in house robber 3, the houses are no longer in the formation of a straight line. Instead, it forms a binary tree. For example, here we have a binary tree rooted at number 3, and 3 has two child, which is 8 and 5. And 8 has a child of 6, 5 has a child of 2 and 3. So the constraint in house robber 3 is the same as the constraint in house robber 1, where the robber cannot rob houses that are next to each other. So in house robber 3, the houses are next to each other only when they are directly connected. For example, 3 and 8 are directly connected, and 3 and 6, they are not directly connected. So in this particular binary tree, we could rob node 3, and since we already robbed node 3, we can no longer rob its child nodes. We can rob node 6, node 2, and node 3, which gives us total money of 14. Optionally, we can skip node 3 and rob node 8 and 5, gives us total money of 13. In this particular example, 14 is the maximum number. So let's derive the inference function for this dynamic programming problem. Let's first index each node in this example from 0. So node 3 will have index of 0, 8 was 1, 2. Let's use Ri to denote the maximum money you can rob from subtree rooted at node I. For example, R2 is the subtree rooted at node number 2, and R1 is the subtree rooted at node number 1. And R0 is actually the final answer we want to give. R0 equals to max of the value of node 0, which is 3, plus node 3 and node 4 and node 5. Since we already robbed node 0, we can no longer rob node 1 and node 2. So we'll have to look one step further from node 0's child nodes. Alternatively, we can skip node 0. Instead, we can rob node 1 and node 2. And the max value between these two options would give us the final answer, which leads us to the final inference function. Note here that we use the val to indicate the value of node I, and L to indicate the left child, and R to indicate the right child. Therefore, the first option would be to rob the node I, and since we rob node I, we have to skip its child nodes, and instead we rob its grandchild nodes, which includes the left node, left right, right right, and right left of node I. Note here, to simplify, we use the I points to L and L to indicate the index of the leftmost grandchild node of node I. So the second option will be to skip node I, and instead we rob its child node, which is the left node and the right node of node I. Similarly, we use the I points to L to indicate the index of the left node. And the value of Ri can be computed by recursively traversing down the binary tree. So let's look at the final code. Here we have the tree node definition, where each node contains a value which represents the money in each house essentially, and each node points to a left and right tree node. So here we have our main rob function, which it takes in a root node. And we have the helper function that takes in two additional integers, which represent the maximum money can be robbed from the left and the right child node from the root node. And in the helper function, we have our base case where we check if the root node is null. If it is null, we just return 0, meaning no money can be robbed. And if the root is not null, we recursively try to rob the left and the right child nodes. Note that while we recursively calling the left child node, we define two integers left and left right to get the maximum money to rob from its grandchild nodes. And similarly when we're recursively calling on the right child node. And by traversing the tree in a post order, we compute the maximum money can be robbed from each root node bottom up. At each level of the tree traversal, we can compute the maximum money can be robbed from its child node and have access to the maximum money from its grandchild nodes, which enables us to take the maximum value out of the two options while we're deriving the inference function. In summary, in this problem, we have houses laid out in a formation of a binary tree where we cannot rob houses that are directly connected to each other. While deriving the inference function, we consider two options. One is to rob the current node and skip its child nodes, and instead consider its grandchild nodes. And the other option is to simply skip the current node and only consider its child nodes. With the property of the binary tree, we can recursively compute the maximum money can be robbed from each root node from bottom up till we backtrack to the root node with the final answer.